So this is an outline for my astronomy class. This is an introduction to astronomy. And so I'm just going to give sort of a brief overview of astronomy and what we're going to be talking about over the next couple of months. Astronomy is the study of what lies beyond Earth, and in particular the objects, but also the interactions between the objects and things like that. It's also an attempt by scientists to compile a history of the universe. We look out and we see the way things are, and we wonder how they were in the past and where they're going to be in the future. And so it turns out that it's possible for us to actively study the history of the universe by looking at distant objects, and I'll talk about that in a little bit. Astronomy is an observational science. Most astronomers are using telescopes and things like that of one kind or another, and photography equipment. It's unlike lots of science where you can do it in a lab. You can dissect a cat or something like that and understand what goes on inside it. You can't dissect a planet, and you can't create planets, and so it's very difficult to study them other than to go look at them. And we can rarely go look at things, and certainly we can't look at anything, at least for the foreseeable future, beyond our solar system, right, which is the sun and its planets. Everything else is too far away. Astronomy goes from the Big Bang until now, and so that's 13 billion years or so. Let's see if I can clear this up a little bit. Okay. So the tool scientists use is called science, or the scientific method, right? And it's a technique for solving problems invented really, or first described maybe by Galileo and Francis Bacon around 1600. Galileo was trying to come up with a way that he could make statements without getting into trouble for them, just making observations and trying to understand how things worked. And so what I'm doing here is trying to tell you that this is not unfamiliar to you, the scientific method. You probably learned about it in middle school or high school, and it's probably something you use to solve problems already. And so in the scientific method, we begin by just identifying a problem. And, as I write here, the problem can be my car won't start, but it could also be how old is the universe, or what is matter in the universe doing, or do galaxies just stay where they are, or do they move? So you can have a highfalutin question or just an everyday question and use the scientific method to solve it. And I would argue that everyone kind of does this already. In science, we have some specific language we use to describe how we do this. And normally we would say we use a hypothesis. My hypothesis is that my car won't start because it's out of gas, for example. In science, we'd say we use a scientific hypothesis, and that specifically means a falsifiable statement. We want the statement to be falsifiable in science so that it can be proven false if it is. And so I could make the statement, Wayne Trail, that's me, is the tallest person in Oklahoma. That's a scientific hypothesis. It isn't true, but it certainly qualifies as a scientific hypothesis, because all it has to be is falsifiable. And all you would have to do is go down the street and find someone who's taller than me and say, ha, your statement is false. And we would get on with our lives. Same thing with your car. You might say, well, maybe my car is out of gas. That's my hypothesis. That's a falsifiable statement. And so we can test the hypothesis. We can check the fuel indicator. Or we could stick something down, a rag or something down into the gas tank. This might not be the best idea in the world, but we could do it and see if it comes out with gasoline on it, right? And that might tell me if I'm out of gas. If the hypothesis doesn't stand up to testing, in any case, right, whether it's a highfalutin hypothesis or a everyday hypothesis, I would have to change it. So, if I find gas in my gas tank, I have to say, well, I have to modify my hypothesis. Maybe my battery is dead, right? Or maybe the alternator's broken. Well, once I have a new hypothesis, I can go back to step 3 and test it again. If my hypotheses were, why do the planets move the way they do? Well, maybe all the planets orbit the Earth. I could test that hypothesis, and eventually, if I were careful enough, I would see that it wasn't true. And so I would have to come up with a different hypothesis. Maybe all the planets orbit the sun, or something like that. In any case, I have to test and repeat, and I keep doing this until I get a hypothesis that I can't disprove. That doesn't prove that it's true. You can almost never prove scientific statements are 100% true, or at least laws. It's always easier to prove things false than true in science, because you just have to find an exception. It doesn't take a committee to say that a law is false. It just takes one diligent scientist to show an exception to the law, and then the law isn't true all the time. So step 4, if the hypothesis doesn't stand up to testing, modify it, and then go back to step 3 again, where you're diligently testing. When your diligent efforts to test the hypothesis don't cause it to fail, you can make a conclusion. Maybe it's a fact. Or, I couldn't find anybody taller than me. I tried my hardest. Or, I'm pretty sure the alternator doesn't work. I'm not 100% positive, but it's the only thing I can come to, and it didn't recharge the battery, and so the car won't start because the battery won't charge because the alternator's broken. And then in any case, once I've done my best, I might have to go to another expert. If it's my car, I take it down to the shop and have an expert look at it, or if I'm a scientist, I can just publish my data or send it off to be published to go through peer review, and maybe somebody else can find out what I did wrong. In any case, if it's highfalutin stuff, if the conclusion is universally applicable, it might become a law, like an object in motion remains that way until acted on by a net external force. That's Newton's first law, right? Or it's a simplified version of Newton's first law. And until we find an exception for that, we just accept it eventually. And it might become called a law. A collection of related laws or facts. A fact is just another successful hypothesis, or we deem it as a fact once it's been tested enough times. We might collect a bunch of related laws into a theory. So the theory of quantum mechanics is a collection of laws describing the physics of very small objects like atoms. Or Newton's theory of motion is a collection of laws describing the physics of everyday objects. Or the theory of evolution is a collection of statements about how organisms or biological matter changes over time. No expert on that. And so on. In popular culture, the word theory is often used in place of hypothesis, and that's where there's some confusion, I think. People often think, well, if something's called a theory, it hasn't been accepted in science. That's not true. So what do scientists do? Right? So scientists use the scientific method and act as detectives. They use known laws and their wits to answer problems posed by nature through the scientific method. Their work goes through peer review, which is examined, questioned, checked, and repeated by other scientists. And that process continues, and it can continue indefinitely. Newton's laws were kind of disproven, at least in certain cases, by Einstein in the early 1900s. So they stood for 250 years before Einstein found some exceptions to them. But now we've acknowledged the exceptions, and we still say for everyday type objects, Newton's laws are extremely accurate. So over the centuries, scientists collect laws of nature. These are just rules describing how the universe works. These are often very useful in understanding the things that we see in science. The laws of nature are often expressed mathematically. Newton's second law is force equals mass times acceleration. And that's lots of laws are expressed that way because often it's much more precise to describe a law mathematically than it is to describe a law just with words, just in a descriptive way. For example, you might know that the model of the atom is the electrons orbit around the nucleus, which contains protons and neutrons, the way planets orbit the sun. And that's a nice picture, but it's not very precise. It's not very accurate. And so we can write down a set of equations that describe that mathematically much more precisely. So that's what's often used. We'll do very little mathematics in this class, but I want to talk enough about it so that we can. We're often dealing with very big numbers in astronomy, and so I want to make sure that we all understand sort of exponential notation. A 10 with a 10 to the fifth power, that's what this 10 with a 5 at the top is called. And that just means 10 times itself 5 times, which is 100,000. 4.56 times 10 to the fourth is 4.56 times 10 times 10 times 10 times 10, which is 4.56 times 10,000, which is 45,600. Here's a negative exponent. Unfortunately, what if I do it this way? If I put a space here, will that help? Ha. So 2 times 10 to the minus fourth is the same thing as 2 times 1 over 10 to the positive fourth. That minus sign just kind of means 1 over. And so that's 2 over 10,000, which is 0.0002. So using negative exponents, we can express extremely small numbers. Using positive exponents, we can express extremely large numbers easily, right? A 10 to the 19th would be a 1 with a 19 zeros after it, right? It would be much easier to write that than it would a 1 with 19 zeros after it. So that's a little bit about exponential notation. Let's see. So let's talk a little bit about observational astronomy. Most of the astronomy we do, as I said earlier, is by looking at light, either with a telescope or the naked eye. And it's important to recognize that looking out at objects is actually looking back in time. Light travels at 3 times 10 to the 8th meters per second, or 300 million meters per second. That's the same thing, or 186,000 miles a second. This means that when you look at something, you're seeing it as it was in the past. The moon, it takes light about 1.3 seconds to get here from the moon. And so this means that when you look at the moon, you're actually seeing it as it was 1.3 seconds ago. Now that hardly matters. 1.3 seconds is not a lot of time for the moon to change. If you look at the sunset, and look at the sun at sunset, don't do it any other time of day. And it takes 8 minutes for light to get here from the sun. The sun is about 400 times farther away than the moon is. And so it takes light a lot longer. It takes about 8 minutes to get here from the sun. And a bigger distance than that is a light year. That's the distance light travels in 1 year. So imagine light traveling 186,000 miles a second for a year, right? Well, it turns out that that is about 6 trillion miles. That's how far light travels in a year. And so the nearest stars are a few light years away. So they might be 10 or 20 trillion miles away. This is clearly much farther away than the sun. Right? In fact, that number is so large it's difficult to wrap our head around it or to put it in any real context. But astronomically, even that's not a very big number. So a light year is about 6 trillion miles. You can see here the Voyager 2, which is the farthest man-made object from Earth, I believe, is about 17 light hours away. And it's been traveling for 40 years. And it's not even 1 light day away, never mind 1 light year. Right? So a light hour is about 669 million miles away. A million miles. A light minute is about 11 million miles. You get the idea. Objects in our galaxy is about 100,000 light years across. And so other galaxies, the Andromeda Galaxy is our nearest sort of neighbor that's comparable in size to us. And it's about 2.5 million light years away. Again, this means that the light that comes to you from the Andromeda Galaxy takes 2.5 million years to get here. So if you were to go out on a dark night in a dark part of Oklahoma or wherever you live, you could naked eye see the Andromeda Galaxy, and the light that goes into your eye from that galaxy was traveling here for 2.5 million years before it went into your eye. Clearly, objects that are farther away than that are the light takes a longer time to get here. Astronomers who are interested in very distant objects are looking. They're interested in the very early universe. Are looking way back in time by looking at very distant objects. So they want to look at galaxies that are billions or even 10 billion light years away. And so they need really big telescopes because these are very faint objects. But when they see them, they're looking at what the very early universe looked like, because they're looking way, 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 way back in time. Okay, let's do a quick tour of the universe, starting with the Earth. Normally, I'll talk about the Earth as about, I would ask you if you knew how big the Earth is. And so try to commit some of these numbers to memory. I kind of expect you to know them. The Earth is about 8,000 miles across. You're going to spend your whole life on the Earth, this ball in space. You should know how big it is. It's about 8,000 miles across. The moon is about a quarter as big. By the way, the ancient Greeks knew these two sizes. They knew the size of the Earth and they knew the size of the moon. And we'll talk about how they knew later on. The moon is about a 250,000 miles from the Earth. The Greeks roughly knew that number as well. And so 250,000 miles away, or a 250,000. The Earth is about 100 million miles from the Sun. So the Sun is 400 times farther away from the Earth than the Moon is. The Moon is a 250,000 miles away. The Sun is 100 million miles away. And so the Sun is 400 times farther away. The Sun is also about 400 times bigger than the Moon. And so those two things kind of cancel out. And in our sky, they look approximately the same size, the Sun and the Moon. Even though the Moon is 400 times smaller, it's also 400 times closer. So down here, I'll say this one, and I'll go to some pictures. The Sun is about 865,000 miles in diameter. Remember, so that's about 100 times the Earth's diameter, a little more, maybe 108. So let me see if I can pull up a few pictures here. So let me just go up to the top of this. Eee. All right. So I'm just going to walk through some of these pictures. These are two interacting galaxies that are hundreds of millions of light years away. They're on a collision course. We'll talk about that, hopefully, if we get to galaxies. This is a nice picture of Mars. You can see Mars has some interesting structures on its surface, these enormous canyons that happened when Mars's crust cracked. Most of our canyons are from erosion, but those are called rift valleys there on Mars. This is an exploded star. This is the Crab Nebula, which was seen by societies all over the planet and marked in 1054 AD. This is the Orion Nebula, which is about 1,400 light years away. It's the nearest star-forming region to Earth. Here's the Hubble telescope. The Hubble telescope is probably the most important scientific instrument in the history of mankind. Single instrument. More science has come out of the Hubble telescope than any other single instrument. There's our friend the Earth. This is the Earth and the Moon drawn to scale. And so the Earth is on the left and the Moon is on the right. Their distances are approximately right and their sizes are approximately right. Contrast that with this picture where the sizes are correct, but the distances are not. They're just stacked up against each other so they'll all fit in the same picture. These distances between them are all wrong. They would be much, 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 much farther apart if the sizes were on this scale. And so you can sort of see this would be how big the Sun is if Mercury was that size and Venus was that size and Earth and so on. You can kind of get a picture of the relative sizes. Jupiter has more mass than all the other planets combined. And the Sun is about 300 times more massive than Jupiter. Um, you can kind of see some of the dwarf planets here, right here and here. We'll talk later on about why the dwarf planets were not called planets. They've been kind of kicked out of the club. Ceres is the largest asteroid, and Pluto, Haumea, Makemake, and Eris are the sort of the largest known dwarf planets. This is a picture of a galaxy which contains billions of stars. It's NGC 1073. NGC stands for New General Catalog. There are ways of cataloging stars and galaxies and so on. It's thought to be similar to our own galaxy. Here's the Milky Way. So this is sort of the plane of the Milky Way is flat, like a disk, like that galaxy that we saw a second ago. And the region here is sort of looking along the plane of the disk. We live in the disk about 30,000 light years from the center, and all the stars are along the plane of the disk. However, there's lots of dust here, and so this dark area through the middle is where stuff has been occluded by gas and dust between us and all the stars that live in there. It's kind of blocking out the stars. Oops. There we go. All right. So we're back to our tour of the universe, and let me just pull some of this up over here. So there are about 10 stars within 10 light years of us. We live in the Milky Way. We just live with up to 1 trillion stars, generally said to be several hundred billion stars. We're about 30,000 light years from the center. There's more matter than meets the eye. We can't account for all the mass in this Milky Way galaxy just by stars and dust. There's stuff we can't account for, and in fact, most of the mass in our galaxy appears to be matter that we can't account for, and so it's an open question. So we call it dark matter because we can't seem to see it. About half of the stars that you see in the sky are multi-star systems. So 2 or 3 stars. I was gonna put another statement in here. You can see about 6,000 stars from Earth with your naked eye. Obviously, if you have a telescope, you can see way, way, way more than that. But it's a tiny fraction of the few hundred billion stars that are in the Milky Way, right? This is the number of grains of sand, of fine sand, in a teaspoon. It's about, just in round numbers, if you fill a hot tub with, or a small pool with sand, the number of grains is about the number of stars in the galaxy. By the way, that's a few hundred billion. This is also about the number of galaxies in the universe. So, fill a hot tub with sand. For every grain of sand, that's a star that's in the galaxy, that's in the Milky Way. And take the same hot tub full of sand, and every grain of sand is a galaxy in the universe. So it's a big universe. And yet it's mostly empty space. Galaxies form as stars do in groups. There are groups of groups called clusters of galaxies, and groups of clusters called superclusters. The total number of galaxies in the universe is estimated to be a few hundred billion. If we talk about small things, so that's big things. To talk about the universe, we also need to talk about atoms. And so I'm going to say a few things about atoms. 1 cubic centimeter of atoms so I said 1 cubic centimeter of water. So this is about a cubic centimeter. This is a dice that's a centimeter on a side, and so it's a centimeter by a centimeter by a centimeter, and so I would call this a cubic centimeter approximately. And so if we took this much water, right, and let me just go back to that, there we go. That much water in that dice that I just showed you would contain about 10 to the 23rd atoms. That's 10 trillion trillion. That's not quite right, is it? It's 100 billion trillion. Anyway, it's a number. It's a 1 with 23 zeros after it. That's just in that much water, right? If I had the same amount of air, a cubic centimeter of air contains about 10 to the 19th atoms, and so that's about 10 million trillion. So that's a lot of atoms, right? That's in our atmosphere. But in interstellar space, it's much different. If you're out in the galaxy somewhere between stars, not near stars, but between them, there's about 1 atom for every cubic centimeter. 1 atom in that box. And then intergalactic space, if you're out in the space between galaxies, instead of just between stars within a galaxy, there's about 1 atom per cubic meter, right? And so that would mean, on average, 1 in every million of these little devices, these little cubes, would have an atom in it. And not, so you can see that most space is empty, right? There's very little matter actually in the universe. It's only when you're around a star or on a planet or something like that that you have a lot of matter. An atom is composed of protons and neutrons in its nucleus, and electrons orbiting around the nucleus. We talked about that a little bit ago. The planetary model of the atom sort of has electrons moving around the nucleus, which contains protons and neutrons. The nucleus, even though it's super tiny, contains, relatively speaking, contains about 99.8% of the mass of the atom. Only a tiny fraction of the volume is in the nucleus, but most of the mass is. If you scale up an atom to the size of a football stadium, the nucleus would be about a dime at the 50-yard line. All of the mass would be in there, but all of the space is taken up by the electrons in their orbits. Atoms are listed in the periodic table, which we'll discuss later. The universe, if you study the universe, which our scientists do and astronomers do, what we find is certain elements are much more common than others. For every million hydrogens, you can see in this table, there are about 80,000 heliums, and then 450 carbons, 92 nitrogens, 740 oxygens, 130 neons, and so on. The universe is so dominated by hydrogen that the others almost don't matter. And certainly once you get past hydrogen and helium, there's not much else. Nevertheless, our Earth is dominated by other elements, silicon and magnesium and iron and so on. And so it kind of depends a little bit on where you are, but if you just take a survey of the universe, hydrogen is by far the most common element. We'll talk about why that is, and what we know about that. All right. That's probably a good place to stop.